Okay, so this video is about the mean value theorem from calculus. It's a very important theorem for calculus students and real analysis students. So let's get started. Mean value theorem. So let's just write down the statement of the theorem. Suppose that f, where f is our function, is continuous on a closed interval I, which is defined as a, b, and also assume that f has a derivative in the open interval ab. Now the theorem says that there exists at least one point, call it C, in the open interval such that f of b minus f of a is equal to f dash of c, where f dash indicates the derivative of f b minus a. Now before we do the proof, it's very useful to see this theorem geometrically. So let's just draw a graph of an arbitrary function f. Let's just label our endpoints a and b. Now what the theorem says that between a and b there exists a point C where the derivative or the slope of the tangent line is equal to the slope of this line segment connecting the endpoints, or connecting f of a and f of b. So the theorem argues for the existence of this point C. And you can see this simply by dividing both sides of this equation by b minus a. So once you divide both sides by b minus a, you end up with this equation, where this is the derivative at this point, and this is the slope of this line segment. So now let's just move on to the proof of the theorem. So let's start off by defining a new function. Let's call it h of x, and we are going to define it as the difference in the value of the function and the value of the line segment that we drew. This is our function, and this is the equation of the line segment. Let's just draw the diagram again. This is the equation number 1 is the equation of the line segment connecting the points, and f of x is just the function. So so h of x is measuring the difference between the function and the line segment. So these differences. Now we know that f of x is continuous on AB, and this whole equation is also continuous on AB, which means that h of x is also continuous on AB. And because f of x is differentiable on AB, and the line segment, the equation 1 is also differentiable on AB, this implies that h of x is also differentiable on AB. Now, in order to derive the equation of the mean value theorem, we have to use something called Rolle's theorem. So if you don't know what Rolle's theorem is, you should read up on it or watch a video on it, because we are going to be using that theorem in this proof. So in order to use Rolle's theorem, we have to evaluate the function at the endpoints, and the function value has to be equal at the endpoints. So h of a is equal to f of a minus f of a minus f of b minus f of a so this becomes 0, so this whole thing becomes 0, and this is also 0, so h of a is equal to 0. And similarly you can evaluate h of b, and h of b will also turn out to be 0. So this implies that h of a is equal to h of b is equal to 0. So the value of h of x at the endpoints a and b is equal to 0. And now let's take the derivative of h of x. Now we know from the statement of Rolle's theorem that Rolle's theorem says that because the value of the function at the endpoints is equal, so there exists some c in the open interval such that the derivative of h at c is equal to 0. Now we know that this c exists from Rolle's theorem, so we don't have to prove it. We can simply use Rolle's theorem to argue for the existence of c. So now all we have to do is take the derivative of h of x, which is very easy because we know it's differentiable. So just use the rules of differentiability that you know from calculus. So this turns out to be f dash of x, and this just becomes f of b minus f of a over b minus a. And now all we have to do is evaluate this at c. So just plug in c, and we know that h dash of c is equal to 0. So just plug in c and see what happens. Now this is 0, so this whole thing is also equal to 0. So all you have to do is equate this equation to 0, and you will obtain the desired result. And you can multiply both sides by b minus a. Simply take b minus a to that side, and that ends our proof. Thank you for watching.